Okay, let's continue our series of limit examples. So I think last time we stopped at number 8, so let's jump right back in there. I think I'm actually going to do a variation of number 8 as well, but let's do it as is first. So it's the limit as x approaches -4 of x squared plus 8x plus 16, all divided by the quantity x plus 4 squared multiplied by x plus 1. Again, the first thing you should do is plug in -4. Well, there I would get -4 squared plus 8 multiplied by -4 plus 16. Because I've got this x plus 4 factor in the denominator, if I plug in -4 there, I'm definitely going to get 0 squared, and 0 multiplied by anything is 0. Notice in the numerator, you'll actually have 16 minus 32, which will be -16, plus 16, that'll give us 0 over 0. So I would think this is probably a good candidate here. So what it means is if we're plugging -4 into the numerator and we're getting 0 out, that tells me that x plus 4 must be a factor. Okay, because otherwise, when you substitute in -4, you wouldn't be getting 0 out. So if I factor the numerator, that actually factors as x plus 4 multiplied by x plus 4. If you FOIL it out or distribute it out, you'll get x squared plus 8x plus 16. Well, we've got x plus 4 squared over x plus 1. Well, x plus 4 squared, that's really just x plus 4 multiplied by x plus 4. So we can cancel out the x plus 4 multiplied by x plus 4 in the numerator with the x plus 4 squared in the denominator. Again, you still have an imaginary 1 on top. So that's going to be the limit as x approaches -4. We've got 1 divided by x plus 1. Well, now I can substitute in this limiting value of -4. I would have 1 divided by -4 plus 1. -4 plus 1 is going to be -3. So I would be left with -1/3 as my solution. So I said I'm going to do a variation of this one. Let's suppose that if I plugged in, or excuse me, I'm still going to do x approaches -4. But now let's do x plus 4 squared, x plus 1. Same thing in the denominator. In the numerator, I'm going to change it. Let's make it x squared plus 8x plus 17 instead of 16. So all I did was change this value. Notice in this case, well, before, if we'd left it alone, we would have gotten 0 in the numerator. Well, now if I plug in -4, I'm actually going to get 1 in the numerator. I'm going to get 0 in the denominator, so now I have to start being a little more careful. And again, what I do is, in this case, so I substitute in -4. Okay, so if I plug -4 into the numerator, you can do the arithmetic, -4 squared plus 8 times -4 plus 17. That's going to give me +1. Okay, I've got, if I look at -4, now this is where I should be a little careful. If I substitute -4 into this factor, x plus 4 quantity squared, the thing that you want to notice is, okay, so really I should be looking at the limit as x approaches -4 from the left, and I should be looking at the limit as x approaches -4 from the right. Okay, so let me write this down. I'll point out the moral of the story here after we're done. Okay, so let's look at -4 from the left. Again, the same thing, just substitute in -4. Again, you get +1 in the numerator. If I do -4 from the left, well, again, if I plug in -4, I'm going to get 0. If I take a number from the left of -4, that means I'm taking values a little bit smaller than -4. If I take something a little bit smaller than -4, like say -4.01, in that case, I'm going to get a number that's close to 0, but it's actually going to be negative. Okay, it's still being squared. And again, if I plug -4 into the second factor, -4 plus 1, that's going to be -3. So I'm actually going to run out of room here. Let's keep simplifying this. So I've got 1 on top. So this says I've got a number that's approaching 0 from the left, so it's approaching 0 but it's negative. If I take a number close to 0 but it's negative and I square it, it's actually going to be a number close to 0 but is now positive. Still multiplied by negative 3. Okay, so now we have to think one more time. I've got a number that's getting close to 0 multiplied by negative 3. Well, it's still going to be close to 0. Originally, it's positive. Okay, it's going to be a positive number close to 0. If I multiply that by negative 3, it's actually going to be a number close to 0, but it's going to be negative. If I take 1 and divide it by a number that's close to 0 but is negative, that's going to be negative infinity. Okay, let's do the same thing. Let's look at negative 4 from the right. Okay, so let's do the same argument. So I still get 1 in the numerator. If I plug negative 4 into this second factor, this x plus 1, I'm still going to get negative 3. Now if I take negative 4 from the right, that's a little bit larger than negative 4. So maybe a number like negative 3.9. Sorry, I was thinking there for a second. Maybe like negative 3.9. If I take like negative 3.9 and plug it in there, well, it's going to be close to 0, but it's going to be positive. And again, I'm going to be squaring it. It's basically the same thing's going to happen. Okay, if I take a number that's a little bit bigger than 0 and I square it, well, it's still going to be close to 0. It's going to be positive. I should say if I take a positive number that's close to 0 and I square it, it's still going to be close to 0 and positive. If I multiply that by negative 3, again, I'm going to get a number that's close to 0, but now it's going to be negative. So lo and behold, again, I get negative infinity. So the solution in this case, the limit as x approaches negative 4, if we just look at the limit as x approaches negative 4, of x squared plus 8x plus 17. So definitely the limit does not exist as a finite number. But you could say that equals negative infinity, since the left-hand limit and the right-hand limit are the same thing. Now, to me, honestly, if I saw this on a quiz or a test, the thing that I would recognize is, okay, it doesn't matter whether you do it from the left or whether you do it from the right. And the reason why it doesn't matter is, okay, I'm going to get 0 when I plug in negative 4. So x plus 4 is going to be close to 0. It doesn't matter if I take a number that's a little bit smaller than negative 4 or a little bit larger. The main thing is because I'm squaring it. Okay? So I know because I'm squaring it, it's still going to turn out to be a number that's close to 0 but positive. If this had been an odd power, for example, x plus 4 to the third power, you would have definitely gotten positive infinity for one of the limits and negative infinity for the other, and then the limit wouldn't have existed. So just want to point that out. So be careful there. When in doubt, check the left and the right limit. Okay, let's look at number 9 now. Let's look at number 9 and number 10. I think those are kind of similar ideas to some extent. So the limit as x approaches infinity, 3x plus 1 quantity squared multiplied by x minus 1 divided by 1 minus x to the third. So maybe you've seen the shortcuts for these. So I can almost do this one in my head. Okay, and let me show you why I can almost do this one in my head. Let's first do it the long way. So really we have to distribute the top. That's 3x plus 1 multiplied by 3x plus 1. That's what 3x plus 1 squared is. So I would get 9x squared. I would get plus 3x, that's plus 6x. I would have positive 1 multiplied by positive 1. That's going to be positive 1. So there's my 3x plus 1 squared. I still need to multiply that by x minus 1. So if I multiply that by x minus 1, I would get, well, let's see, 9x to the third minus 9x squared, and then 6x multiplied by x, that'll be positive 6x squared. I would get negative 6x. Then I would have positive x, and then I'd have negative 1. So let's combine. This is 9x to the third. I guess we'll have a negative 3x squared. Negative 6x plus x is negative 5x minus 1. Okay, so really we have the limit as x goes to infinity of 9x to the third minus 3x squared minus 5x minus 1. I'm going to give myself a little space here, and you'll see why in just a second. So this is all being divided by 1 minus x to the third. So maybe you've seen the shortcut, and again, I'll talk about that at the very end. If you don't know it, this is kind of the idea. And this is a common technique, especially when you're doing limits as x goes to positive infinity. It could also be going to negative infinity. We would do the exact same thing. So the idea is you look at the denominator, and I look at the highest power of x. Well, okay, in this case, it's easy to pick out because there's only a single term involving x. It's x to the third. What I do is I divide every single thing by x to the third, by x to the third. And then I simplify. So I've got the limit as x goes to infinity. So this is 9x to the third over x to the third. That's going to leave me with 9. I've got my negative there. There's my 3. X squared divided by x to the third would be negative 3 over x. 5x divided by x to the third, that would be negative 5 over x squared. And then I would have I would have minus 1 over x to the third. So again, I'm just breaking it up. 9x to the third over x to the third, 3x squared over x to the third, negative 5x over x to the third, negative 1 over x to the third. The denominator, I would do the same thing. I would have 1 over x to the third power. And then I've got negative x to the third over x to the third. That would leave me with negative 1. Now the idea is, well, x is getting big. I'm putting in larger and larger and larger and larger numbers. Well, if I take, for example, 3 and divide it by a really big number, so 3 divided by a really big number, a number going to infinity, that's going to approach 0. So the idea is 3 over x, that's going to get close to 0. 5 over x squared, that's going to get close to 0. 1 over x to the third, that's going to get close to 0. 1 over x to the third is going to get close to 0. So I've got 9 minus 0 minus 0 minus 0 over 0 minus 1. Well, I'm left with 9 over negative 1, which is going to be negative 9, and that's my answer. So really the reason why I said I could do this in my head at the very beginning is I noticed, okay, if I take 3x and square it, I think, well, I'm going to get 9x squared, right? If I take 3x and I square it, I'm going to get 9x squared. If I multiply that by x, I'm going to actually get x to the third. And I know if I distribute this out, all the other stuff that I get when I distribute it out, everything else I get is going to be a lower power. It's going to be something less than x to the third. So I think, okay, if I multiply out the numerator, I'm going to get a 9x to the third, and then a bunch of stuff that has lower degree. Well, and then in the denominator, I've got this negative x to the third. There's a rule or a theorem that says if the degree of the numerator is equal to the degree of the denominator, and if you're doing a limit as it goes to positive infinity or negative infinity, if the degree of the top equals the degree of the bottom, the answer is going to be the ratio of those coefficients. So the coefficients are 9 over negative 1. That ratio works out to be negative 9. And hey, that's my answer. So this one I could do, by recognizing that the degree of the numerator is going to be the degree of the denominator. If you don't recognize this, this is the algebraic way to show it. This way of dividing by the highest power in the denominator, more generally what you're doing is you're dividing by the thing in the denominator that gets biggest the fastest. So let me look at my other examples here. Where'd they go? I'm missing them. I don't know if we have some others like that. I don't think I do. So let me show you how you can use the same idea. So I said we're only going to do 17, but man, this is going to turn into a lot more. Let's suppose we had something like the limit as x goes to infinity of e to the 2x minus e to the x over e to the 3x plus e to the x. Something like this. Okay, so this isn't a rational function. A second ago, this is a rational function, a polynomial over a polynomial. Okay, so as x goes to infinity, each one of these exponents is going to go to infinity. 2 times a big number is a big number. 3 times a big number is a big number. Remember the graph of e? It looks like that. Recall e is just a number. It's roughly 2.71. So e is just a number. So I've got, again, if you're really approximating it, you could say I've got 3 to a large power. Well, this is going to be infinity minus infinity over infinity plus infinity. The numerator's indeterminate. Anything could really be going on here. Okay, who knows what's happening? Well, I can use the same idea. I can look at the denominator, and I think of e to the 3x and e to the x. If I put in, say, like x equals 1,000, which one of these two terms would be bigger? Well, e to the 3x would be bigger than just e to the x. E to the 3,000 would be larger than e to the 1,000. So this is what's called the dominant term. It's the one that's getting biggest the fastest in the denominator. I would use the exact same idea. I would divide everything, in this case, by e to the 3x. So I'd have e to the 2x divided by e to the 3x minus e to the x over e to the 3x. I would have e to the 3x over e to the 3x plus e to the x over e to the 3x. So I'm doing the limit as x goes to infinity. Okay, again, you just have like bases here, so don't be thrown off by the e's. You know, if it was x squared over x to the 5th, I would say, oh, I've got like bases. I would do 5 minus 2. I would get 1 over x to the 3rd. Same thing, I've got like bases here. They're all e's. So I would do e to the 3x minus 2x. That would leave me with e to the x. Same thing for the next one, e to the 3x. So e to the x divided by e to the 3x. If I do 3x minus x, I'm going to have 1 over e to the 2x. Anything divided by itself is 1. Then I've got e to the x over e to the 3x. That's going to be 1 over e to the 2x. So we just said that, you know, as x goes to infinity, e to the x is going to go to infinity. So that's 1 over infinity minus 1 over infinity over 1 plus 1 over infinity. And again, infinity is not a number. It's not a number. So all we're saying here is that as x approaches infinity, you're going to have 1 over, you know, you're going to keep getting larger and larger numbers in the denominator. 1 over a large number is 0. Then we've got 1 plus, well, 0. You would have 0 over 1, and that would give you your solution of 1. Excuse me. Oh, gosh, I'm losing my mind. Give you your solution of 0, making sure you're paying attention out there. So 0 over 1 is 0. Wouldn't that be tragic? You get all the way, do all the hard stuff, and then you put down a 1 on the test, and then your mean old grumpy teacher gives you a bad grade. Okay, let's look at number 10. We've got 4x minus 3x over 5x. The same idea here. If this had, like, you know, a 5x plus a 2x down here, I would use the same idea. I would say, so just to kind of relate this to the ones we just did. And I'll let you do this one. You can do this one on your own. If it was this limit, so suppose I had 5x plus 2x, I would do the same thing. Each one of these terms, 4x, 3x, 5x, 2x, those are all going to get big as x goes to infinity. But 5x is going to be the dominant one. So in this problem, if I had to justify, I would divide everything by 5x. This one's a little bit, you know, I don't know if you'd say easier. Just the observation you can make here on this problem is, well, I've got a single term in the bottom, so I can always just break this up into two fractions. So the limit as x goes to infinity of 4x over 5x minus 3x over 5x. Well, 4x over 5x, I could write that as 4 over 5 raised to the power of x. 3x over 5x, that's going to be 3 over 5 raised to the power of x. And now, again, I have to stop and think. So this is where kind of number sense comes in. And when people say number sense, they basically mean think about what's going on with the arithmetic. So if you have good number sense, it means you are good with arithmetic. So as x gets bigger and bigger and bigger, well, I'm going to have 4 fifths times 4 fifths times 4 fifths times 4 fifths times 4 fifths. I'm going to be subtracting away 3 fifths times 3 fifths times 3 fifths times 3 fifths times 3 fifths. The thing to recognize here is if you take a number that's greater than 0, it could be greater than or equal to 0, as long as it's strictly less than 1, if I take the limit as x goes to infinity of that number and raise it to the power of x, If I take a number between 0 and 1 and multiply it by itself, what happens? Let's suppose k was 1/2. Well, if I take 1/2 times 1/2, what do I get? I get 1/4. So actually, it gets smaller, right? A fourth is smaller than 1/2. Suppose I have 1/2 to the 3rd power. It gets even smaller. I get 1/8. So if I take a number between 0 and 1, again, greater than or equal to 0, strictly less than 1, if I start multiplying it by itself, it's going to get smaller, smaller, smaller. This limit is going to get closer and closer to 0. That's the argument here. If as x goes to infinity, 4/5 raised to that power is going to get closer and closer to 0. 3/5 to that power is also going to get closer and closer to 0. That limit is going to work out to be 0, and you're done. Intuitively, maybe that seems plausible, because as x gets really, really big, yeah, the numerator is going to be big, but the denominator is going to be so much larger. A number divided by a number that's much bigger is a small number. It's close to 0. So again, number sense. All right, so I'm going to stop there, and we'll do at least 11, probably 11 and 12 in the next video, because those both deal with logarithms, and then we'll jump on to probably then I'll do another video involving the ones with trig, and then I'll do one last video involving, so 16, 17, and 18 all involve a limit that involves the number e.